Hi, hi everyone. This is Prof. K speaking, and today we're going to talk about phase transitions. Our learning objectives for today are to define phase transitions and phase transition temperatures, to explain the relation between phase transition temperatures and intermolecular attractive forces, and describe the processes represented by typical heating and cooling curves and compute heat flows and enthalpy changes accompanying these processes. And I'm going to go in a little bit of a different order than the book, but we are covering pretty similar content. So you can follow along with me, or you can read the book to help you out with this. But here we go. So phase transitions. So this past week, we talked about different phases and how they relate to intermolecular forces. And today we're going to name the processes by which we move between different phases and talk about how we describe them quantitatively in terms of temperatures, in terms of enthalpy, in terms of the amount of heat it takes to move between these phases. So if you start as a gas, you can either go to a liquid via condensation, or you can go directly to a solid via deposition. And so these are two ways that we can transform gases into the other phases. If you start as a liquid, you can either go to a gas via vaporization, or you can go to a solid via freezing. Solids, if you start as a solid, you can get to the other phases via melting to get to liquid, or sublimation to get to a gas. And so if we think about water, which is what I've pictured here in this graphical format, we can go between these different phases, and we often think about water as melting from ice to form liquid water, and then vaporizing to form a gas. And oftentimes when we talk about CO2, and we'll have dry ice that goes directly into a gas at room temperature. And today we're going to talk about how we know which processes we might see at different temperatures and pressures, and how we explicitly name them in terms of the temperatures at which these processes will happen. So just to recap what I said on the last slide, vaporization involves molecules moving from the liquid phase to the gas phase, while condensation is the opposite and involves molecules going from the gas phase to the liquid phase. So the condensation you see on the outside of your glass versus how your sweat evaporates, vaporization. Melting is when molecules in the solid phase move to the liquid phase, so like ice melting. Freezing, molecules in your liquid phase move to the solid phase. You put liquid water in your freezer and you get ice cubes out. Sublimation is when a solid goes directly to a gas phase. And deposition is the opposite, where you take gas molecules and you create the solid phase. And so all of these are the names for the processes that we observe as we move between these physical states. And they label the phase transition, or the transition between one phase to the next. One of the ways that we can look at phase transitions is to look at what are called heating and cooling curves. And what this heating and cooling curve is a plot of temperature for different phases as you add heat to our system. And so when we start at the bottom left of this corner, we have solid ice. And the solid water is heated and its temperature increases, but it stays solid until it reaches its melting point. At its melting point, the heat that it's absorbing doesn't relate to the temperature rise, but instead it causes the material to transform from a solid to a liquid. Then you can heat that liquid for a while until we get up to the boiling point. And then all the heat that we put into our system goes into transforming that liquid into a gas. Once all of the liquid has been evaporated or vaporized, then we're left with a gas which we can continue to heat up. And so as we're adding heat, we can change the phase until we undergo, or we can change the temperature of a phase until it starts to undergo a phase transition. But how do we know how much heat we need in each of these steps? If I wanted to know how much heat takes to turn a solid ice cube at -10 degrees Celsius to liquid ice at 60 degrees Celsius, how much heat do I have to put in? And how do I know how do I describe this temperature where phase transitions occur? And so last semester, we did talk a little bit about how if you have a particular phase of a material like solid ice, we can describe how temperature could change between maybe -3 degrees and -10 degrees. And we use this equation, which you may or may not recognize, where we have the mass, the specific heat of the material we're discussing, and the change in temperature. But as you can see from the plot, where you're in this sort of blue chunk down here, where you're transitioning phases, you can't use this equation because there's no delta T, and we're undergoing a different process than simply heating up one material. So in this slide deck, I'll talk about how we describe the other portions of this heating curve and what sort of language we use to talk about the processes that we're interested in with respect to phase transitions. So to start, we'll look at vaporization and condensation. And one of the vocabulary words that we're going to practice using in this section is vapor pressure. And vapor pressure is the pressure exerted by a vapor in equilibrium with a liquid in a closed container at some temperature. And so this definition implies a couple things. One is that it's very temperature specific at a given temperature. So we need to know a temperature to have a vapor pressure, which tells us that vapor pressure is probably dependent on temperature. But what this means by the pressure exerted by the vapor in equilibrium with the liquid in a closed container, what this effectively means is what balance of gas and liquid do you have at an equilibrium in your sample? And so at the beginning of this picture, we have our liquid and none of the molecules is in the gas phase yet. And so what happens is the molecules start to escape and form this gas, but it still has some space in the container for more gas to form. And so what happens is it continues to release vapor until it reaches some pressure, and that change in pressure can be recorded using this change in height of some other part of the system, which we're not focusing on right now, but effectively what we're saying is that there's some equilibrium height that this will settle to if you give it time based on the fact that some of the gas molecules escape the liquid and apply pressure to the liquid. And I use the word equilibrium here, and what I'm specifically referring to is a dynamic equilibrium. And what that means is that when we reach state C, it's not that no gas is leaving and is leaving the liquid or that no gas is returning to the liquid. Instead, at this equilibrium point, the rate of our vaporization is equal to the rate of condensation. So the amount leaving the liquid to become a gas and the amount leaving the gas to become a liquid are equal. These rates are the same. And so the amount of gas and the amount of liquid stays the same, even though there's some amount going back and forth. And one of the reasons that we talk about vapor pressure is because vapor pressure can help us identify boiling points. And so a boiling point is the temperature at which a liquid's equilibrium vapor pressure is equal to the pressure exerted on the liquid by its gaseous surroundings. So on Earth, we define our vapor pressure as 101.3 kilopascals, because that's equal to 1 atmosphere. And we can use that pressure to say that where the vapor pressure of a particular compound is equal to that 1 atm or 101.3 kilopascals, the temperature where you cross that pressure is your boiling point. So ethyl ether's boiling point is close to maybe 35 degrees Celsius. Water's boiling point is 100 degrees Celsius, which you might remember. Ethyl alcohol has a boiling point of around 80 degrees Celsius. And so we can use this vapor pressure to help us determine a boiling point at a particular pressure, which on Earth is 1 atm. And we can see from this plot that the vapor pressures, or these lines that move across this plot, that the vapor pressure that a system experiences is dependent both on temperature and also on what the compound is. So I'm going to talk a little bit about both of these, and we can use that to understand a little bit why boiling points are the way they are, which is connected to what we talked about last week, where we described boiling points in terms of intermolecular forces. So temperature's effect on vapor pressure and boiling point is that if you increase the temperature of your system from low temperature to high temperature, what you've done is you've increased the kinetic energy of the molecules on average, and that increased temperature means that more molecules can escape than they could before. And if more molecules can escape, then that means that your equilibrium pressure between the gas and the liquid, as we talked about in the last slide, so this is our gas, and this is our liquid, the vapor pressure will increase with temperature, which is the same thing we saw on the last slide, was that as we increase our temperature, our vapor pressure increases because more of our liquid is leaving and forming a gas at equilibrium. And then if we look at intermolecular forces effect on vapor pressure, or effectively how the structure of a particular compound affects vapor pressure or boiling point, is that compounds with higher intermolecular forces or higher attraction will have lower vapor pressures because fewer molecules can escape the liquid phase. So if you're talking about if you look here, if you compare at 20 degrees Celsius, the vapor pressure of water is quite low compared to the vapor pressure of ethyl ether. And so if we think about this in terms of intermolecular forces, H2O versus ethyl ether, H2O can participate in hydrogen bonding and dipole-dipole bonding and dispersion, whereas ethyl ether can only participate in some dipole-dipole interactions. So because water has much stronger intermolecular forces than ethyl ether, its vapor pressure is also significantly lower at the same temperature. And so this relates to what we talked about last week, in that if something has high intermolecular forces, it's also going to have a higher boiling point because it takes more heat being put into the system before those molecules will start to leave the surface of the liquid. And so this is another more graphical way of representing what we discussed next week, and it specifically connects the concept of vapor pressure to that process of boiling. And so one of the other ways that we can do it if we don't have a nice plot like this is we can also determine boiling points from vapor pressure directly using the Clausius-Clapeyron equation. And so here, our vapor pressure is some function of a constant based on a chemical, and then an exponential dependence on the enthalpy of vaporization, which we're going to talk about in just a second, and the gas constant and the temperature. And so if we think about this on the last slide, it says that the pressure of our system is going to have some relationship to the inverse of the temperature. And this is helpful because if we want to find the boiling point of an equation, we can plug in a pressure that we want our vapor pressure to equal to as 1 atm. And then we can look up in a table the constant based on the chemical. We can determine the enthalpy of vaporization or also find it in a table. And we have the gas constant, and that helps us find the boiling point temperature. We can also use the Clausius-Clapeyron equation to help us identify what would happen if I changed a system from being at P1 equals 1 atm and a temperature of 20 degrees Celsius, and I increase the pressure of my system to 2 atm. How does that change the temperature of my system with respect to vapor pressure? And so we can use it to find this equation. And so this term, the enthalpy of vaporization, we'll talk about a little bit. But what the enthalpy of vaporization is the energy needed to turn a liquid into a gas. So vaporization is endothermic. It needs an energy input. So if you want to take a pot of water and turn it into a gas, you're going to need to put a lot of heat in. And that makes it endothermic. And I've cited chapter 9.3 here, so that if you'd like to go back and review endothermic, you can. But ultimately, this heat of vaporization is the amount of energy per mole here that we need to convert some liquid into a gas. And then the reverse of this, or if we wanted to turn a gas into a liquid, is the energy involved in turning that gas into a liquid, the enthalpy of condensation. And this is exothermic, which might feel strange because when you think about something turning from a gas into a liquid, you would think it's getting colder. And that's consistent with this being exothermic, because what it means is that if you want this process to happen, you're going to need to take energy out of your system. So you need to cool the system and take that energy out to drive this reaction forward. And so that's why the enthalpy of condensation is this negative 44.1, which is the opposite of the enthalpy of vaporization. And so what this allows us to do is it allows us to return to this curve that we had before, where we can describe these portions in red using the change in temperature for a given state. And now for vaporization, we can say that the heat of creating gas from a liquid for this compound is how many moles of that liquid we have multiplied by the heat of vaporization, or the energy per mole we need. And so this allows us to capture this transition, and the Clausius-Clapeyron equation helps us connect that to calculating a boiling point temperature, which helps us identify where on this plot this will occur. And for the other processes on this plot, which is the freezing or the melting of this, is we also have enthalpy of fusion, which is used to describe melting. It's just another word that we use to describe melting, which is the energy needed to turn a solid into a liquid. And this process is once again endothermic. If you want to melt ice, you have to put heat into the system. The enthalpy of freezing is the opposite, which is the energy involved turning a liquid into a solid. And this is exothermic because we're going to have to take energy out of our system to get it to cool off so that it can form the solid. And we have melting and freezing point here, which we don't have sort of the equivalent of vapor pressure in this system, but what we do have is that it's the temperature at which that solid and liquid are in equilibrium. So you have the rate of solid melting, of solid to liquid. It has to be equal to the rate of liquid to solid. So this is another dynamic equilibrium that we have here. And where that equilibrium happens is the melting point or the freezing point. So once again, on this heating curve, we can now say that to move in this blue chunk, the number of moles of ice we have to melt multiplied by the enthalpy of fusion, or how much energy it takes to melt that ice, is going to be the heat of that process. And for this plot, we've been talking about water, and we've specifically been looking at pressure of the system, where we have water going to a liquid and then a gas as it melts. But if we have a system where we skip the liquid phase and we go straight from a solid to a gas or a gas to a solid, we also have similar enthalpies for sublimation and deposition, which is the energy it takes to turn a solid into a gas, which is once again endothermic. You have to put a lot of energy into the system to do that transition. Or enthalpy of deposition, the amount of energy you have to remove to turn that gas into a solid. And so this should say deposition here, not freezing, but it's effectively the same, but same type of enthalpy, but just for a different process, this gas to solid. And so overall, we can describe our process as so at the beginning I asked, how would we describe a particular, so we want ice at -10 degrees turned into gas at maybe 115 degrees Celsius. So if we want to do this, now what we can do is we can set up this system of equations that we have, and we can move through this plot. So we start as a solid, and we're going to have that solid, and we're going to heat it up using MCS delta T, so until we get to the melting point temperature. So this first delta T here is going to be the difference between the melting point temperature and where we started. And then we'll have to convert all the moles we have of that compound into this heat using the enthalpy of fusion to see how much heat it takes to move through this line. And once we finish that, we can then start to do the difference in temperature between the melting point and the boiling point. And we can do that in terms of the MCS delta T. But instead, we use a specific heat for the liquid, which is different than the solid, because solid water holds a different amount of it has a different specific heat, or it changes its temperature in a different amount with the addition of more heat. It can hold a different amount of energy. So we have to use its specific heat here to help us see how much heat it would take to move through this red portion. And then we have to use, this should be enthalpy of vaporization to go from the liquid to a gas multiplied by the number of moles we have in our system. And then once again, however much energy we want to continue to heat up the gas, we'll use MCS delta T, but of the gas here. So overall, we can use vapor pressure to help us identify where boiling points are happening and to help us determine heats of vaporization. And we can look at the dynamic equilibrium between liquids and solids to help us identify melting points. And we can use these equations to help us understand how we move across these charts through heating and cooling curves. And you can imagine if instead of going from a solid to a liquid, we could go from a gas to a liquid, or we could go downwards in this process. And then your final and initial temperatures will just change based on the direction you're going. And so this is how we'll start to navigate some of these problems and look at how much energy we actually have to put in to a phase transition to get it to happen, and start to describe how our temperature changes as we put this energy into our system.